So good morning friends, again welcome. Since long time we have not met for the lecture purpose. I was a little bit busy, but I hope we will be covering the syllabus, whole syllabus. Uh, let's remind the things what we are learning nowadays. We are learning nowadays is that chemical equilibrium. In chemical equilibrium, we have seen the different terminology, that is Gibbs free energy, standard Gibbs free energy, uh, enthalpy of formation, etc., etc. So we have seen in the last lecture the problem regarding this topic. Okay, today we will see the more problem regarding this Gibbs free energy, calculation of the Gibbs free energy. The next problem is calculate the standard Gibbs free energy. Remember that it is the standard Gibbs free energy, means it is at the standard state. Calculate the standard Gibbs free energy change for the following reaction from the data provided. That is, reaction is 2SO2 in the gaseous state plus 2 plus O2 plus O2 in the gaseous state, that forms the 2SO3 again in the gas form. The data is given at 25 degrees centigrade, means it is at the standard state, and pressure is 1 atmospheric pressure, 1 bar pressure. Substance SO2 gas, delta H0 of F means standard enthalpy of formation. Standard enthalpy of formation, the value is minus 297 kilojoule per mole, and standard entropy, that is 248 joule per degree Kelvin per mole. For SO3 gas it is minus 396, and standard entropy is 257, that is positive value, and O2, that is it is already in the standard state, therefore delta H0 of F for this O2 is 0. We are already discussed about this, and S0 for this O2 is 205 joule per degree Kelvin per mole. Now what do we have to calculate? This data is given. Okay, what do we have to calculate? The standard Gibbs free energy change. Standard Gibbs free energy change, how we write? We are given standard Gibbs free energy is equal to delta G0 delta H0 minus T delta S0. This delta H0, standard enthalpy of change in standard enthalpy, right? Delta S0, it is change in the standard entropy. Therefore, delta G we can calculate, right? From this given data, what we have to do is we have to first calculate delta H0. Now we know that delta H0 is given by this equation. Delta H0 is given by this equation. That this equation we have already learned this equation. What is that? Delta H0, that is standard enthalpy of standard enthalpy change. Delta H0, it is the summation of number of moles of product, summation of number of moles of product, delta H0F, standard enthalpy of formation of product, minus summation of NR, number of moles of reactant, delta H0 of F of the reactant. Delta H0, standard enthalpy change of formation of the reactant, right? So to delta H0 of F3 SO3 gas, we are talking about here, it is in the product, right? Product minus reactant. Why 2? Since there are 2 moles of product molecules, therefore 2 moles of product molecule, standard enthalpy of formation of product minus 2 moles of SO2 gas. This one is what? This one is reactant. 2 moles of SO2 are there. Therefore, this one is reactant. SO2 is reactant. Minus, why minus? Again one more reactant is there. This reactant O2, right? It is summation. It is summation for SO2 plus O2. Therefore, minus sign, right? Minus O2 delta H0 of FO2, that is in the gaseous state, right? Therefore 2 multiplied by 2 moles of the product multiplied by standard enthalpy of formation of SO3 gas is minus 396. That is data is given minus 396. SO3 is minus 396. This is the product molecule, right? Minus 396 minus 2 moles of SO2 gas multiplied by minus 297. Minus 297, it is given SO2 gas. Standard enthalpy of formation of the SO2 gas, the value is minus 297, right? Minus 1 mole of why 1 mole, since in this reaction only 1 mole of oxygen is there, therefore 1 mole of oxygen multiplied by 0 kilojoule per mole. Why 0 kilojoule per mole? Since oxygen is in the standard state, we already told you that oxygen is in the standard state, therefore the standard enthalpy of formation of the standard state molecule is 0, therefore this value is 0. Therefore this value, total value comes out to be 0. This value, total value comes out to be 0. If you multiply this and subtract the value, we will get the minus 198 kilojoule per mole. Minus 198 kilojoule, that is value of delta H0. That is value of delta H0, right? Now next, what we have written the equation is this equation we have learned. Delta G0 is equal to delta H0 minus T delta S0. What next? The temperature we know that at 25 degrees centigrade. Delta H we have calculated. Next thing is this temperature we know. Next thing is we have to calculate the delta H0. Now we have also learn how to calculate the standard entropy change of formation. Standard change in entropy for the formation of the molecules, right? Standard entropy change of formation, right? So it is again summation of number of moles of product, and of the entropy change of that product minus summation of number of moles of reactant. Now number of moles of product, 2 number of moles of product we have seen in this reaction. There are 2 number of moles of product, therefore 2 into S0 of SO3 gas, this is the product molecule, right? Minus 2 into this is for the reactant molecule, 2 into S0 of SO2 gas minus 1 into S0 of O2 gas. These are the reactant molecule. Therefore 2 multiplied by 257, where the value is coming from, this 257 standard entropy for the SO3, that is given in the data, 257 joule per degree Kelvin per mole into, this is for the reactant molecule, 2 multiplied by 248. 248 is coming from this value, the already value is given, multiplied by minus 1. Why? Because the oxygen is only 1, therefore multiplied by 205. 205 standard entropy change of the oxygen molecule, 205 joule per Kelvin per mole. Therefore if you add the value, it is the elementary mathematics, multiplication and addition. If you add the value, the delta S0 of F comes out to be minus 187 joule per degree Kelvin. Minus 187 joule per degree Kelvin. What we have said that? We have to use to calculate the Gibbs free energy change. Standard Gibbs free energy change is equal to delta H0 minus T delta S0. Delta H0 we have calculated, delta H0 we have calculated. Therefore putting the value of temperature, putting the value of delta H0, putting the value of delta S0, we can calculate very easily the standard Gibbs free energy change for this reaction. This is what? Minus 198 kilojoule is what? the delta H0 value. This is equation number 1. Suppose this is equation number 1 and we are putting the value in the equation number 1. Therefore, this value minus 198 delta H0, we have kept this value here, minus 298 is what? Temperature is given 25 degrees centigrade, right? Plus 273, that is equal to 298 degree Kelvin. 298 degree Kelvin. What is the formula? Delta G0 is equal to delta H0 minus T delta S0. There is the 0. T is temperature, that is here 298 degree Kelvin multiplied by 187. 187, this value is coming from here. Delta H0, standard entropy change of formation. Delta H0, right? 187 multiplied by 1 into 10 raised to minus 3. Why 10 raised to minus 3? Because this value is in the kilojoule. This value is in the kilojoule. To convert this value, joule per degree Kelvin, we have to divide by 1000. We have to divide by 1000 means we have to multiply it by 10 raised to minus 3. Therefore, this value comes out to be, if you add, multiply this value, its value comes out to be plus 55 kilojoule. I am talking about kilojoule. If this value comes out to be 55 0076 like that, and if you round up the value to the kilojoule, if you multiply, then it comes out to be 55 kilojoule. Therefore, if you subtract and addition these values from the higher value, lower value get subtracted. Therefore, delta G0 for the above reaction, that is change in Gibbs free energy, standard Gibbs free energy, change in standard Gibbs free energy comes out to be how much value? Minus 142 kilojoule. Minus 142 kilojoule. There are other more problems in the textbook. You can see the problems regarding this. But as I told you that the problem will ask in the exam about 40%. If the text is asked in the exam, it's 60%, and problem they can ask in the exam 40%. So without solving problem you cannot pass. Therefore, remember that while solving the question paper we have to solve the problems. Therefore, remember that problems are very important. Now, our today's next topic is chemical equilibrium. Chemical equilibrium. Chemical equilibrium. Chemical equilibrium. Now, chemical equilibrium. Wait for a moment. Chemical equilibrium. Now, remember that we learn lots of reaction during 11th standard, 12th standard. You have learned. Suppose A of reactant and B of reactant, they are reacting together. They are forming C and D. These are the product. C is the product. D is the product. Right? We can say that this A and B, if we mix together in the round bottom class, in the RB, in the round bottom class, in the RB, this suppose X A is the X reactant and B is the Y reactant, and if you mix together, and there is a formation of the product. Suppose, right? When we are calculating the stoichiometry of the reaction, stoichiometry of the reaction, stoichiometry is what? Stoichiometry is how much quantity of A is taken, how much quantity of B is taken, how much quantity of C is formed, and how much quantity of D is formed. Or there are many reaction A, that is only one reactant molecule, and there may be the formation of 2-3 number of products. And remember, there may be the 2-3 reactant molecule. There may be the 2-3 reactant molecule. There may be the formation of only one product, D product. Only one product. There may be the 4 number of reactant molecule, and 4 number of reactant molecule, only one number of product may be formed. There may be the only 2 reactant molecules and only one number of product may be. There may be only 2 reactant molecule and 2-3 number of products may be formed. 2, 3, 4, etc., etc. 3 to 4 number of product molecules will form. Then what we do in the stoichiometry is that, what do we do? We calculate how much liter of A reactant molecule is taken, how much liter or kilo, or if it is in the gas, we can say that how much liter. If it is in the solid, how much kilo, right? Kilogram, milligram, gram, etc., etc. That is weighable form, right? That is measurable form. We take the reactant molecule and products are formed. Products are formed, right? When there is a plus B or any reaction, there is formation of C. When this reaction will stop? Reaction will stop whenever one of the limiting reagent will exhaust practically. Limiting reagent. The reagent on which the reaction depends, that is called as the limiting reagent. Whenever there is the exhaustment of or end of the practical end of the one of the reactant molecule, there we can say that the reaction is practically stopped. The reaction is practically stopped, right? Practically stopped. There are n number of reaction, most of the reaction, lots of the reaction, most of the reaction follows these rules. What rule they follows? They follows if one of the reactant is ended, one of the reactant is exhausted, we can say that practically this reaction is stopped and there is a formation of the product. Right. If only one reactant is there and C plus D plus etc., etc., 4-5 number of products are forming, what we can say that when the reaction is stopped when this A, concentration of A is negligibly small or practically small. Or we can say that practically this reactant A is exhausted. We can say that this reaction is stopped, right? We know that. Now remember that there are many reactions which can go backward direction. There are many reactions which can go backward direction. What we are talking about? We are talking about the chemical equilibrium. We are talking about chemical equilibrium. There are many reactions A plus B that gives C plus D. Again, this C plus D will react together. They form the A plus B. Now, for this A plus B reaction, C plus D are the product, A plus B are the reactant. For C plus D, they are forming the product A plus B. These are the reactant at that time. When there is a reversible reaction. For example, if we mix together NO2 gas plus NO2 gas, there is a formation of N2O4. there is formation of N2O4. Again, this is the gas and this is the gas. There is formation of N2O4. Mixed together means what? Mixed together means it is the one and the same. NO2 is one and the same. This NO2 is one and the same. We know that. All the gases molecules of the same gas molecules, those are having the identical property, right? These two are not the two different gases. This is the only one gas, right? Then if you take this one gas, if you take this gas in a evacuated tube, this is the tube, suppose glass tube is there. If you take this gas in the evacuated tube, suppose in the glass tube, this gas NO2 gas is brown in color, dark brown in color, NO2 gas is dark brown in color. At the initial stage, evacuated tube is there. At the initial stage, this dark brown color disappears. In the evacuated glass tube, this dark brown color disappears, and this colorless gas N2O4, colorless gas is formed. But if we keep this mixture NO2 and N2O4 for longer time in that glass tube, what will happen? The disappearance of this dark brown color again reappears, and for longer time, if we keep for longer time, there is equilibrium between this colorless gas and dark brown gas. Which means that whatever amount of this colorless N2O4 gas is forming, that is again converting into the dark brown gas, means this reaction is called as the dimerization reaction. This reaction is called a dimerization reaction. Dimerization what? Two molecules of gas combined together, there is formation of one molecule, but N2O4, it is the dimerization reaction, right? Again, this colorless gas is converting into the dark brown gas, and there exists the equilibrium between this dark brown gas and colorless gas. Means what? The reaction is going to forward direction as well as backward direction. In that case, we can say that the reaction is at equilibrium position. Then, now, what is the question? Question is that this is only one gas. Suppose this is 2 liter gas and this is 2 liter gas, and if we keep in the evacuated glass tube, there is a formation of N2O4 definitely, right? There is a formation of N2O4 definitely, means this 2 liter is not, this 2 plus 2, that is equal to 4 liter was the original concentration. After forming this colorless gas, some of this 2 liter, that is 4 liter, converted into suppose 1.5 liter, right? Again, this 1.5 liter is converting into the NO2. Again, NO2 is converting into the N2O4. There is the equilibrium. We can say that there is a formation of product as well as reactant, right? We can say that there is a formation of reactant as well as product. What is happening at the molecular level is that molecular level we can see from the glass tube that the dark brown color disappeared and white colorless gas is formed, that is dimerization. This white colorless gas is formed, converting into dark brown. It is forming, but the reaction will stop somewhere middle. Means we can say that there is a mixture of colorless gas as well as dark brown gas. What is happening at the molecular level? This N2O4 continuously converting into the NO2, and this NO2 continuously converting into the N2O4. But we can recover this N2O4 from that reaction mixture by different process, by separation of the gaseous molecule. Right. Next example we will see that. Next example we will see that what is H2O. Sorry. H2O in the gaseous form, that is vaporized form, वाफ, पाण्याची वाफ, H2O in the gaseous form plus CO in the gaseous form, carbon monoxide in the gaseous form at high temperature, at higher temperature, there is a formation of H2 in the gaseous form plus carbon dioxide in the gaseous form. The reaction is stoichiometrically perfect. Right? Stoichiometrically perfect means number of moles of products that are forming, right, is equal to number of moles of reactant molecules, the atoms that are taking part in the reaction, that is equal to the product they are forming, right? So this H2O in the gaseous form, that is steam, H2O in the gaseous form, steam, we know that H2O exists all the three form, steam, that is gas, liquid, that is water, and solid, that is ice, right? CO, that is carbon monoxide in the gaseous form, there is a formation of H2 plus CO2. What is happening? Suppose stoichiometry, we are talking about stoichiometry. Suppose this gas is 5 liter, this gas is 5 liter, and the product that is forming H2 gas, suppose this gas is 3 liter and this gas is suppose 4 liter. I don't know exactly what is the stoichiometry. 4 liter product is formed. What is happening? Again, this hydrogen and carbon dioxide, they are combining together. They are again reforming the H2O plus CO, that is carbon monoxide. Means what? Suppose we have mixed together this H2O and CO, and there is a formation of H2 and CO2. That H2 and CO2 again converting into H2O plus CO, right? But at a given instant, suppose this reaction is we are carrying about in a cylinder, in an evacuated cylinder, the cylinder is sealed one, right? H2O plus CO, that is forming H2 plus CO2 gaseous. If we withdraw the sample from this gas cylinder, we can get the all the four molecules, that is H2O, CO, H2, CO2. We can get the mixture of all these four. Therefore, we can say that there is a formation of the product and there is formation of the reactant molecule also. Right? So, what is happening? What is happening? If you plot the graph of concentration versus time, suppose this side concentration, what is? It is number of moles of reactant molecule, concentration this side, and time this side, time. If you plot the graph, what is happening? The reactant molecule, this is the concentration of reactant molecule. Reactant molecule goes on decreasing, and the product that was initially 0, the product molecule goes on increasing. Right. These are the reactant molecule, H2O plus CO, carbon monoxide, and these are the product molecule, H2 plus CO2, gaseous. This is gaseous. This is again, it is in the gaseous state. Right. Right. When these are the products. These are the products. And these are the reactant. What is happening? the concentration of the reactant, this graph, the concentration of the reactant is not going to be 0, and the concentration of the product is not going to be the more than this concentration of the reactant molecule. This is the gas. So what is happening, this state, after some time, if you keep this reaction mixture for longer and longer and longer time, there is the equilibrium between concentration of the product. This is the concentration of the product, and this is the concentration of the reactant. Reactant चं concentration less झालेले, right? Reaction चं concentration less झालेले, product चं concentration वाढलेले. But after certain limit, the product concentration will not increase and the reactant concentration will not further decrease. It will not go to the 0. Why? Because the reaction again is going to the backward direction. Means again there is a formation of the product. Right? But this product will not be 100% forming again, because again form reactant, again that is converting into the product. Such reactions are called as the equilibrium reaction. Such reactions are called as the equilibrium reaction, or such type of equilibrium is called as the chemical equilibrium. Now, what we are learning in the thermodynamics is that when how much equilibrium this reaction will form, this reaction will form the equilibrium that is having the minimum Gibbs free energy. Minimum Gibbs free energy. The reaction will stop where? Minimum Gibbs free energy of the reaction. To keep the minimum Gibbs free energy for this reaction, at that time the equilibrium will be attained. Whenever there is a minimum Gibbs free energy for that reaction, the reaction will reach to the equilibrium. Remember that. We have seen that when delta G is negative, the reaction is spontaneous. When delta G is positive, the reaction is non-spontaneous. But for this chemical equilibrium or equilibrium type of reaction, there is the minimum Gibbs free energy. Right? In the next lecture, we will see the different laws of mass exchange. Remember that nowadays your exam forms are started. I will be covering our entire syllabus. Till then, bye bye. Thank you.